Hello and welcome. I'm going to test the audio first before we start. Alright, the audio works fine, but there is a phase delay between the mic and the video, so hopefully it won't create too much trouble. So in this video I'm going to very glancingly present the library IEEE 1284, the IEEE 1284 module library from the ElectroKIO, the first library to be introduced to the ElectroKIO project. Well, first of all, this video is a part of the episode, the Electrostatic Sandbox SDK. For those who don't know, the Electrostatic Sandbox SDK is an in-home SDK, the complete software development kit suite that is contemplated to be written purely in C, and it should have an interface for the IEEE 1516 standardization for distributed simulation systems. The name for this standardization is the high-level architecture standardization, and it is used among many things like a lot of distributed systems, like the military defense systems, the NASA distributed simulation systems, and among others. Anyway, the point that we have, the project is subdivided into, let me just grab this first, just take this out from here, and we have this, just read this. Now this is the architecture that we have, the ElectroSim project, the ElectroNetSoft project, and the ElectroKIO project. Right? The IEEE 1284 is a part of the ElectroKIO project for the parallel port control. Let me first, this is the actual content for this video. Quickly, we want to glance over the physical model for the library, which is based on the first order logic, and the Super I/O chip documentation, the conceptual model for the library, and the application logic that if you build your application using utilizing the parallel port, how do you do this? This model is for the architecture of the applications. And then hands-on testing, final hands-on testing. As you can see, we have the a multimeter here, and this is the board. These are the outputs of the boards. And I guess, well, you find the link to the GitHub, which is there, which is already there. This one here, you'll find this attached to the description. All right. So let me first start by recalling out the physical model for the library. So the physical model for the library, unfortunately, that I have erased the model before capturing a screenshot of it. So it's really hard now to grasp the model again. But anyway, I will try to find some more time to get into this later. All right, and you will find, hopefully you will find that in the documentation of the library, because I still haven't figured out the full documentation for the project. So anyway, if there exists a Super I/O chip, that Super I/O chip has the name IT8720 or 20F or whatever. There exists an IT and Super I/O chip, or for all Super I/O chips, there exists a parallel module. such that the parallel module presents an interface for a data register module, a status module, and the control module. So you have a large component, which is the Super I/O chip, that is not a part of the library, but you have a subset, which is the actual module for your parallel port communication. That module is present on the Super I/O chip, and so this part here. And then the module has subdivisions or subsets, all right? It has 3 types of registers. So this was the first design, which is a control register, a status register, and a data register. But we actually have erased those, and I didn't actually delete those. But anyway, we are now using a power port register, and this is a generic power port register. So this could be represented as a data register, could represent a data register, is a placeholder for data register, status register, or a control register. It's a placeholder for the bits to change and manipulate before actually entering them or before using them into the library. So before actually using them here, for example, in the right control bit or in the right data bit. So we have we have functions for each couple of function table for each register, right? So we have a couple or a set of functions that control the data register. Those here controls the data. Those controls the data register. There is another one which writes to the data register as a whole. This one here, and others which control the control registers, and finally the actual this one is with a control register, and finally with the actual status register, which is the status register is a read-only register. So this is the actual physical model, right? It's composed of the module, and the module is composed of 3 registers. That's it, very simple basically. Now let's move on to the other part, which is the actual interesting part. This is the IEEE standard signaling method for a bidirectional parallel peripheral interface for personal computers, IEEE STD. This is the 1994 file from the IEEE, right? This part is the interface concepts. As you could see here, the concepts of physical link and data levels originate from the Open Systems Interconnect model developed under the auspices of the International Organization for Standardization, ISO, and promulgated as ISO 7498. Anyway, the IEEE-1284 interface separates the operation of the link between the host and the peripheral from the data communicated over that link. So we have basically a separation in logic between the operation of the link itself. So this part here, this is the link, the cable itself, or the data bus, and between the host, it's obviously the motherboard or the Super I/O chip, and the peripheral, which is your module that you want to build here over the GPIOs. All right, so it's basically separated the operation of the link between the host and the peripheral from the data communicated over that link. So conceptually, the data is separated from the link itself. Right? The data is separated through software. That's the point. And through the negotiation modes that were there for the printer cable. So you're going to have a lot of things in this file anyway. This is 110 pages, so it covers a lot about the negotiation and the handshaking signals in the old parallel board. But this is not the point of this library. I will talk about the vision later on, and how you're going to use the ElectroKIO into this. But anyway, you got the point that we have a data level and link level. First of all, we have the hardware or physical model, which is a host and the preferred, right? And then you have an application on the host, and on the peripheral you have an I/O manager, which is also an application. It also could be an application, or it could be plain hardware. It could be an application if you connect these to a microcontroller, for example, an AVR chip. So it depends on your use cases. In most cases, it is an application. It is an actual application, all right? And there is a physical connection, which is this port. This here, there's a physical connection is analogous to the link level, right? And the data level is a part of the software connection, which is a logical connection. This logical connection. So you have to separate the library. Actually, what the library do is that it separates the actual logic from the actual physics. So it separates the logical connection from the physical connection, so that you have a library, a shared object file that you could use in your application without dealing that much with the actual code of the library. Let me check for the video. Yes, working fine. Now the point is this is very good if you want to build an application that will utilize this one, that will utilize the IEEE-1284 Module library from the ElectroKIO, right? So I will just read these parts, such as IEEE communication mode negotiation to be. So this allows link layer functions, such as the negotiation layer, to be localized in an interface driver that transports the application data without having to interpret the data stream, right? So ideally, the application and the preferred personality should have an open dialogue. The application, the part of the application, and the part of the personality should have an open dialogue. The personality is the part where you find the my library here. So my library actually sits here beyond, it's actually on this side. The library is actually on this side. On the device, it's above the device driver file, because the device driver is a part of the Linux kernel. It is. So my library is not a part of the Linux kernel, nor a part of the application development, but it is a middleware. It is a kernel space. It utilizes kernel space APIs. So it should be a part here. That is below the application and above the device driver. All right. The personality is typically maybe the behavior of your preferred. So it might be the behavior that your software on the peripheral I/O manager or in your microcontroller chip, how this like the routines or the programming routines of how your peripheral will deal with the application. Right. Anyway, after having an open dialogue that allows them to exchange the information as needed, and this is the application logic, right? The IEEE-1284 interface provides a means by which this dialogue may be achieved. There are differences in the way that application and the personality communicate. As I told you, the application, as I've told you, the application is your application on the motherboard, for example, or in the GNU Linux environment, and the personality is the other application on the microcontroller, for example, or your hardware interface that is connected directly to the GPIO ports or the digital out ports of the parallel port. The interface drivers in the host and the preferred deal with the details of selecting an appropriate communications mode or modes, hiding the interface dependencies for, and this was for the sake of the old printer data line. The new one, you will define your own routines of communication on the host and the peripheral. Now, let's get to the to a more interesting point, which is some hand-on and linked to GitHub. You already know this. So anyway, the Sandbox project, the ElectroKIO part is for kernel user interface or user space APIs, and this would be the first library here. As you could see, we have the electrostatic core. The core has a source, the source has the include, and include the ElectroKIO, and this is the header that we have. And those are the bins or the bits predefined. And then we have the ElectroKIO here. This is the source file. This will be the source code for the library. And those are for the old printer data line. This is a host compat handshake mode. This is obsolete. Literally, they are obsolete. You could do this on your own using the write and read, using the write controls part. Anyway, now this part is the initialize. It initializes the mode. Let's terminate the mode. Initialize the callbacks for operation success and failure. Open. This opens the port. Close the port. Release the port. Let's release the memory. This releases the memory acquired by the port, and this loads the mode of the parallel programming mode. There are a couple of modes. This is also obsolete, but I have to do it anyway. The claim, this is very important because this signals the operating system that the current process need to claim the port, and the port has to be not busy in order to, has to be free in order to claim it. Right? There is another one which is reclaim. It tries to reclaim the port, and if it fails, it will return. But I didn't actually implement that. Anyway, there is write controls, a way to. This is a good algorithm to operate on the bits to extract. Let me see here. To extract the bits from your register. So you pass in a register with bit settled on or off, and then it goes here onto this gate, and then if it is on, which is 1, we will shift it using this using the number for the pin 0, which is this one here. So it will not be shifted. It is the first bit anyway, and so on and so forth. So this creates a way that we operate elementarily on each bit. This algorithm helps us to operate elementarily on each bit. So this is an elementary operation, and then we add those bits before pushing them to the memory. All right. The same way we do this demarshalling algorithm here on the right, on the read. This is the read one, and the same way goes over and over again. So anyway, I wanted to quickly test, because this is just a review and not a quick tutorial, but you will find an example there. This one here is an example. This one is a good example for this part. So I do have an operation success, and it returns with a caller, and then it routes to the function of concern. And now we have as I've said before, the actual physical model that we have presented: a data register, a control register, and a status register, which is not presented here. And they are actually using the same type that we have defined, but the instances differ eventually, right? So we define the mode also. Well, the mode, if not defined, it will default to the standard parallel port mode. This is the extended compatibility mode. This is the latest mode, the extended compatibility mode of the board of the standardization. So first of all, we initialize the callbacks, and then we open claim. So if we didn't claim this, this process will fail. These processes will fail. These commands will fail. That's the point. And then we try to write data and write controls. Now look at this part here. We write data. When we write data, we write at bit 7, which is the purple pin here on this test case. We write on and on the other off. Right? So let's start our multimeter and see. Okay. No sound. Great. Let's see this connected to which pin there. Right. Well, it is connected to the actual purple one. I see. Yes, to the purple one here. And let's run the test. And we test this. And we got a simple problem here. Let's just clear those for now. Test again. And we got a problem reading it. So I think this part, because there is a couple of problem writing permissions. So let's give the permission for the parallel port device. And give it a permission. Let's run again. Test again, and it didn't work. Well, I got the problem mainly with the actual part that adds. So I guess this